back at example 2. Why don't you go ahead and show me, if you can, what your derivative graph looks like? I'm wondering, does it look sort of like this? All right, well, let's take a look. Let's take a look at some of the key features of this graph, of the derivative graphed here in green. And one of the things that we talked about is right here, the slope's got to be 0. And I can see here, it crosses the x-axis as 0 there. Same thing at 2 and the same thing at 4. So the first part of this graph that I want to kind of examine is everywhere where the derivative is above 0. And that is in between 1/2 and 2 and to the right of 4. Everywhere the graph here is above 0, that means the derivative is positive. And if the derivative is positive, derivative is a slope. Slope's a positive. And remember, we visualize positive slope as going upwards, that it's increasing from left to right. And that's exactly right. So that's the very first thing that we're going to highlight here, is that anywhere our derivative is positive, then that means our slopes are positive, and that means the function is increasing in those areas. Okay? All right, well, the next part is going to be just the flip side of that. Look at this part of the graph. To the left of 1/2 and in between 2 and 4, here our derivatives are negative numbers. And since derivative is supposed to be associated with slope, when our slope is a negative number, then that means that the graph's supposed to be decreasing. Look at this part right here. Yes, it's a parabola, but don't worry about the fact that it's a parabola. There's something else that's going to be happening here at this point. But the fact that this is all negative means that our graph needs to be going downwards in between 2 and 4, and it definitely is. It's going downwards. That's the next thing I want to make note of. Everywhere where my derivative is negative, then that means that my graph's going down, the slopes are negative, and that means my function must be decreasing. And you may remember in pre-calculus, when you had to dissect a function, you had a graph of a function, use your calculator, and you found the intervals over which the function was increasing or decreasing, but you depended upon the calculator in order to figure those things out for you. Now we're going to be able to use calculus to figure it out for us. All right, the last thing is this. Last thing is going to be super important. It's going to be critical, and that's where our slopes are equal to 0. And that was right there at point C, there at point B, and again here at point A. Slopes are 0. This means, okay, when you have a slope of 0, what kind of line do you have? Don't you have yourself like a horizontal line? And that's exactly right. You have a horizontal tangent line. And look at what kind of points those are. So right here, we've got one of these relative minimum points. And then right here, we've got a relative maximum. That's going to be highly significant. Now, eventually what we're going to do is this kind of thing in reverse. In other words, I have a picture of the derivative, and then I want to be able to tell some aspects, some key aspects of the graph of the original function. That's going to be something that we definitely work towards both in this unit and in the next one. Okay, so let's take a look at some of the notations, different competing notations for derivatives in calculus. Now, we have mentioned before that two of the key figures that are associated with the discovery of calculus, one of them is Newton over here. He was in England working on calculus at the same time, roughly, that Leibniz over in Germany was working on calculus. Completely unknown to each other, right? So they kind of discovered it around the same time, but you could probably imagine if you're writing something down and somebody else is writing something down, you might write it down a little bit differently, even if it's covering the same exact topic. So we've got different kinds of notations. So here's the first one. First one is the Lagrange, named after a mathematician. Lagrange notation is the prime notation. It's the one that we've seen before. I read that one as f prime of x. Now, and I also read it as like the derivative of f, and since x is the independent variable, with respect to x. Or maybe I can have a y that I'm taking the derivative of. The name of the function's y, it's y prime. Okay. Leibniz notation, though, is a lot different from this. There's no little prime marks. It looks like this. dy dx. And it looks a little bit like delta y over delta x, and that's where it comes from. So I just read this dy over dx. I don't even say over. I just say dy dx. dy dx. The derivative of y with respect to x is how you interpret that. The derivative of y with respect to x. Now, my function may not be y. And so maybe it's f or g or something like that. So Leibniz has another one for that one. Again, this is the derivative with respect to x of f of x. So I can put my function in here, and then this on the outside is, it acts like an operator. It tells me to take the derivative with respect to x of this particular function. And when I say with respect to x, that's just indicating, it's indicating the independent variable that we have in that function, okay? And then Euler, I think maybe you've heard of Euler before. Euler did lots of stuff in mathematics. He also did some stuff in calculus. He came up with his own notation. One of the notations that we use, that we name after him, is that letter E for the number E, 2.71, blah, 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 business. He came up with that notation. It's called the Euler number. Anyway, and so we have an operator, again, capital letter D means derivative. The subscript here is the same thing as it is here, same thing it is here, same thing it is inside the parentheses here. It's indicating the independent variable. So the derivative with respect to x, and whatever you put inside the brackets there, that's the function that you're taking the derivative of. Hey, what's derivative again? Did you say slope? Yes, you're right. All right, so here's Newton's notation. Newton, who's given lots and lots of credit for discovering calculus, of course, like nobody uses his notation. Look at it. It's a dot. It is a dot up above the y. It kind of looks like this, right? Except for these little dots, as you keep taking more and more derivatives, you just have to keep piling on these dots. He called his a fluxion. And this is almost like the flux capacitor, if you've ever seen the Back to the Future movies. Anyway, fluxion. Specifically, this is a derivative with respect to time. Derivative with respect to time. Here we're doing derivatives with respect to x. And there are some branches of physics that still use this notation, but we are not going to see it in our book, and we're not going to see it on the AP Calculus exam. The ones that we will see are the Lagrange prime notations and the Leibniz dy dx notations. These things are used so incredibly frequently on the AP exam. We want to be able to recognize them, understand what they are. Now, let me go a little bit further here. Boop. And this is speaking about the Leibniz notation. The dy dx, where it comes from is this. Dy dx comes from taking the limit as delta x approaches 0 of delta y over delta x, changing y over changing x. This is the slope of a secant line, and when we take the limit as this delta x approaches 0, the difference between our x's approach 0, that's our h value, right? I get the derivative. I get the dy dx. And so you can see the relationship between those two notations and why it makes sense. It makes complete sense from the delta y over delta x. Okay. Now, if I want to find the derivative at a particular point, when it's Lagrange, I just put the point in here, f prime of 3, say. And there's nowhere to put it in here in the Leibniz notation. And so we add a little something to it. This means the derivative with respect to x, the big slash, vertical slash, means such that x is equal to a, whatever the x value that we want to find the derivative of. So the derivative of y with respect to x at x equals a. All right, I got a couple more things for you, and that's words associated with this process of taking the derivative, which is called differentiation. It is basically the very first, I'm going to say, new operation in mathematics you've learned in quite some time, differentiation. All right, so let's look at a couple words associated with this. First one is differentiate. It is a verb. To differentiate means to take the derivative of a function, all right? And then we have the noun version. Differentiation is the operation that's defined by taking the derivative of a particular function, all right? A function is differentiable. Oh, now we have an adjective. A function is differentiable at a point if the derivative exists at that point. So we've got a verb, we've got a noun, we've got an adjective, All right, and then here we have a function is differentiable on an open interval from a to b if its derivative exists at every single point in that interval. It's differentiable on an open interval if it's differentiable at every single point in that interval. Right? And then, here's some sample intervals. Maybe it's differentiable everywhere. Maybe it's just differentiable from some key point, like 0 to infinity. Or maybe on the other side of it, from infinity to some other values, from infinity to 1, let's say. All right, in the next couple of examples, we will actually we haven't actually found the derivative of a function yet. That's coming up.